Hey guys, Dean Chase here with another geometry lesson for you. It's good to have you all back. We're finally jumping on to chapter 2. I hope you guys are ready for this. It's probably my least favorite chapter if I'm being honest, but we have to know this stuff. It's important to get us through the rest of geometry. So without anything else to say, let's just let's bow our heads for prayer and get started. Dear Heavenly Father, I want to thank you for this day, Miss Lord. I want to thank you for all you've done. I want to thank you for my students. Thank you for all you do for us, Lord. Thank you for being so good to us. We love you. In Jesus' name I pray, amen. Alright guys, so today we're going to be learning how to use inductive reasoning. Okay, this is lesson 2.1, page 72 in your book if you're following along with me out of the same geometry book. Let's get started, okay? Geometry, like much of science and mathematics, was developed partly as a result of people recognizing and describing patterns. In this lesson, you will discover patterns yourself and use them to make predictions. Pretty basic. Let's keep going. Describe how to sketch the fourth figure in the pattern. So, the first thing I like to do when I'm looking at this type of thing is kind of to see what's going on. So here we have one purple, one green, okay? And the next one, we have two purples and two greens. Or we went from 2 to 4. So if I'm thinking, I'm like, hey, that just doubled. So then let's take a look at the next one. We have 4 purples and 4 greens compared to 2 purples and 2 greens. So it doubled again. So we went 2, 4, 8. So logically, if I'm thinking, I'm saying the next one's probably going to have 2, 4, 8, 16 different rectangles. So I'm going to draw a square and divide it up equally into 16 different rectangles. And then I'm going to alternate shading every other one. So to save you guys and not put you through the misery of seeing my handwriting, I've already typed up the words for you and you could just write it down that way. So each large region has twice as many equal regions as the previous figure. Sketch the fourth figure by dividing a square into 16 equal-sized vertical rectangles. Shade alternate regions. Okay, hope that makes sense. Whenever I'm doing reasoning like this, I just like to look at it for a minute. I always feel like super brain power, like I'm studying, you know, putting it to work. And you guys can do it too. Let's keep going. So, example 2. Describe the pattern in the numbers 1,000, 500, 250, 125, and so on. And write the next 3 numbers in the pattern. So, if I'm looking at this, the first thing I do is I say, how does 1,000 get to 500? And right off the top of my head, I could think of 2 different ways to go from 1,000 to 500. I could do 1,000 minus 500, which would give us 500. Or I could do 1,000 divided by 2, which would also give us 500, or splitting it perfectly in half. So I'm going to take that reasoning and try and apply it to the next number. So the next number is 250. Well, my first thought was if I subtract 500, I go 1,000 to 500 by subtracting 500. Well, 500 minus 500 would give us 0. That's obviously not 250. But if we divide 500 by 2, that does give us 250. So it looks to be that we're dividing by 2. So we're going to try it one more time. 250 divided by 2 is going to give us 125. So I'm going to say each number is divided by 2. That's the pattern we're looking at. Now they want us to write the next 3 numbers. So 125 divided by 2, 125 divided by 2 is going to equal 62.5. Okay, that's the first number. Now we're going to take that number again. 62.5 divided by 2 is going to equal 31.25. take and divide that number, 31.25, divided by 2 gives us 15.625. Okay, so the next three numbers are going to be circled in green. Not bad, right? It's actually kind of fun just exploring. This is the type of mathematics where you get to feel like an explorer and get to try and figure things out on your own, just like the original mathematicians were doing. So, inductive reasoning. A conjecture is an unproven statement that is based on observations. You use inductive reasoning when you find a pattern in specific cases, and then write a conjecture for the general case. Okay? So, let's keep going. Given the pattern of the triangles below, make a conjecture about the number of segments in a similar diagram with 5 triangles. So like I said, I like to just see what's changing. This triangle has 3 sides, right? Here we have 2 triangles, and how many lines do we have? We have 1, 2, 3, 4, 5. So I'm going to go 3, 5. This has 3 triangles, and it's 1, 2, 3, 4, 5, 6, 7 sides. So if you look, each time you add a triangle, you're actually adding 2 more segments. So if we want to know how many segments are in a similar diagram with 5 triangles, we know it would be 7, which is the 3 triangles, plus 2 for the 4th triangle, plus 2 for the 5th triangle. So it's going to have a total of 11 segments. Yeah. So the conjecture could be every time we add a triangle, we add 2 additional, oops, sorry folks. We add 2 additional segments. I don't know what happened here, folks. I'm just going to wipe that out for you. Okay. Numbers such as 3, 11, 15, and 29 are odd numbers. Make and test a conjecture about the product of any 2 odd numbers. So, I kind of like to do this in reverse order. I'm going to test the product of these odd numbers we have given up here. I'm just going to write the list down the side. So I'm going to do 3 times 11, which equals 33. 3 times 15, which equals 45. 3 times 29, which equals 87. Okay? Then I'm going to do 11 times 15, which equals 165. 11 times 29, which equals 319. Lastly, we also have 15 times 29, which equals 435. And now if I look at this grouping of numbers, I'm going to see if I notice anything about them. Do they have anything in common? Well, they don't all start with a 3, that's for sure. But if I do look, they are all actually odd numbers. So my conjecture, which I've tested, could be the product of any 2 odd numbers will be an odd number. And that is true. If you multiply any 2 odd numbers together, it's going to come out to be an odd number. And we proved that. That's pretty cool. Disproving conjectures. To show that a conjecture is true, you must show that it is true for all cases. Whew, that could take a long time. But you can show that a conjecture is false, however, by simply finding one counterexample. A counterexample is a specific case for which a conjecture is false. So guess what? That's what we're going to do in example 5. Find a counterexample to disprove the conjecture. Supplementary angles are always adjacent. So there's two things we're looking at here. We're looking at the word supplementary, and we need to know what that means. Supplementary means two angles add up to equal 180 degrees. I wanted to ask you a question because that's what I do in my class. But supplementary angles add up to equal 180 degrees. And then we're going to look at the word adjacent. Adjacent means that two angles are going to be touching each other, okay? They share a common vertex. So we know that we could have two angles that are supplementary that are non-adjacent, and that's how we could form disprove our conjecture. So let's do, and I'm just drawing it. These are not exact angles. This is going to be an angle that is 100 degrees. If one angle is 100 and we want the angles to be supplementary, the next angle is going to have to be 80 degrees, okay? Which is just a hair under 90. So I'm trying to draw it kind of how it'd look. And this is going to be 80 degrees. Well, right here, we have drawn two non-adjacent angles that are supplementary. So not all supplementary angles have to be adjacent. We just disproved that conjecture. Pretty simple. So, example 6, our final example for the day, and then we're done. Which conjecture could you make based on the graph? So here we have a graph, which is the drama production participants. Our y-axis is showing us the number of drama production participants, and it's going up by tens. And then the years that they had the productions. Okay, so let's just go ahead and read through these. A, participants have remained steady since 1984. So in 1984, it was at 20, and it dropped down, and then it went up, and it's kind of leveling out. I'm going to tell you, not true. It has obviously not remained steady with this drop and climb. The number of girls participating in drama production exceeds the number of boys. I don't know how we'd know that because our graph doesn't say whether it's boys or girls. So once again, this is not a true statement. I mean, it could be, but we don't have the information to actually know that. The number of participants for West Side Story is over 50. Does this say anything about West Side Story? Nah. So definitely not that one. So hopefully D is going to be right. Otherwise, we're paddling up a creek, going up a creek without a paddle. I'm going on a float trip on Wednesday, and I'm pretty excited about it. So I got canoeing on my mind. D says participants have increased steadily since 1990. So 1990 is right here. And sure enough, we never had a decrease in participation. It was always increasing. So, D would be the conjecture you can make. Guys, not a bad lesson. I hope that I explained it well. Power through this chapter with me, and chapter 3 and on, we're going to have a blast. So just carry along. Feel free, you're my students, not my students, to subscribe so you know when I post a new video. Also, I always try and do the end screen of my video to the next lesson, so feel free to jump ahead. If you're my students, I encourage you to watch the next one, get ahead. And you guys, I love you. Have a good day. See ya!